This is video 34 in the lectures on the design of reinforced concrete beams. This is a calculation example of torsion reinforcement. Consider a concrete cross-section with 3 diameters 25 as tension reinforcement and 3 diameters 10 as compression reinforcement. The beam has a depth of 600 and a width of 300 and is loaded with a torsion moment and a shear force. The shear force is 140 kilonewton. The point of gravity of the shear force is 64.5 millimeters, but we need the diameter of the stirrup, which we are just looking for, because it's torsion and shear force together. Instead of taking diameter 8 or 10, we will take our first gamble as diameter 12. So with diameter 12, but we have to check it if this is okay. It's 46.5, so the effective depth of the section is 535.5. The shape factor is then 1.61, and smaller than 2. The minimum shear stress is 0.39, and the minimum shear force capacity is then 63 kilonewton. We calculate now the shear capacity of the concrete only, VRDC. For VRDC, we have to calculate the rho L, the density of the longitudinal reinforcement, and we arrive at 0.009169. Mu is 0.528. And then VRDC, it is CRDC multiplied by the K factor and so on. And we have 94 kilonewton. 94, compare it with the VRDC min. So we take 94 as the real value, and it is smaller than the 140 of VED. So we need stirrups. And we need stirrups for the amount of ASW over S bigger than this value. The alpha is 90 degrees. So we take vertical stirrups, and we have 0.334 square millimeters per meter. This is the needed reinforcement for the shear force only. We have to check the concrete strut, so VRD max with cotangent theta equals 2. We arrive at 611, so the 611 is more than the maximum that we have in our beam, so that's all right. It means that the cotangent theta 2 is well chosen. Otherwise, we have to decrease the cotangent theta 2. The additional tension in the tension reinforcement is then the minimum of the two. It's and if we calculate the minimum of the two, we find 140 kilonewton. This is for the tension. This is for the shear force. For the torsion, we have 65 kilonewton as torsional bending moment or torsional moment. The capacity of the section is 2 AK FCT times T effective. We first have to, FCT is 0.7 times FCTM, it's 1.35. And the equivalent thickness of the section is the maximum of 2 times the location of the reinforcement, or AC divided by U. And if we plug in the numbers, we see that the effective depth of the effective width of the section is 129 millimeters. So we calculated, or we took the rectangular section of the beam and converted into an hollow core section with a an effect with a depth of 129 millimeter. The area AK within the inside the section is 80,541 square millimeters. UK, the circumference of AK is 1,284 millimeters. Then the capacity against torsion of the concrete only equals 28 kilonewton meter, but we have 65 applied, so we need torsional section reinforcement. And ASW over S, the additional shear reinforcement that we need is then 0.464 square millimeters per meter. We have to check the concrete struts, TRD max with it's given by this formula. If you put in the numbers, you have 88 kilonewton meter. So the maximum that you can take is 88, or the concrete struts cannot handle it, but the applied is 65, so this is okay. The additional longitudinal reinforcement that we need for the whole circumference, the whole total of the circumference, is 2,383 square millimeters. So it must be evenly distributed in the whole circumference of the section. The total needed stirrups equals then the stirrups needed for shear force and those for torsion. It means that we need a total of 0.8 square millimeters per meter. In choosing the stirrup reinforcement, we must take into account the maximum distance that the stirrups can have. And the maximum distance, it's for the shear force 0.75D. For the torsion, it's U over 8, and it's always the minimum of B and H, the width and the height, or the width and the depth of the section. So we see that the minimum distance is 225. Now, when we take a diameter of stirrup of 12, we started with it in the beginning of this exercise, so we'll continue with that. And then we plug it in this formula, make it equal to 0.8, then you see that we need 275 millimeters. So if you put in 275 and 12, you have 0.823, so that's bigger. So that will be good. The diameter 12 with space with two legs, and a spacing of 275 will be all right. Now, this spacing was okay for shear force, but it's not okay for torsion. So in fact, when we have got that, it means the diameter 12 is too big, because you should reduce the 275 to maximum 225. You cannot go further on. But if you take 225, you have too much stirrup reinforcement. So in fact, we should now repeat the exercise with a diameter 10 instead of 12. We will just see how we will handle that. But for the moment, we continue with 12. We know that the maximum torsional moment is 0.88. That can be taken by the concrete struts. The maximum shear force is 611. So this is okay for the applied torsional moment and applied shear force. We do the unity check for the total, and we have 0.97, so it is okay. Now we will have a look at the cross section. we know that we have 3 diameters 25 as tension reinforcement, 3 diameters 10 as compression reinforcement. Let's consider the top reinforcement now. The minimum reinforcement that should be put there is 242 square millimeters. Torsion says that we need 2,383 additional longitudinal reinforcement, but evenly distributed along the circumference. So we will take 8 locations, we divide by 8, and that means we need 298 square millimeters. Of those locations, it is 1, 2, 3, 4, 5, 6, 7, 8. So it means that for the top reinforcement, we need for torsion 2 times 300 is almost 600 square millimeters. But already available is 3 diameters 10. So we take the maximum, the 3 diameters 10 or the 596, and it gives me 596, so it's 3 diameters 16. So we did not add up here the 3 diameters 10 with the longitudinal reinforcement needed for torsion. Why? Because this compression reinforcement was there as a minimum reinforcement. It was not there because it was needed for one reason or another. If this minimum reinforcement is really needed for taking loads, then you must add them up. So the 3 diameters 16 will be fine. Then the bottom reinforcement. For bending, in fact, what we need is 737 square millimeters. For torsion, again, is the total divided by 1, 2, 3, 4, 5, 6, 7, divided by the 8 positions. It's again 600 square millimeters because we have here 2 contributions of the longitudinal reinforcement. Then for shear, we need an additional 140 kilonewtons divided by 435, 322 square millimeters, and it gives us 1,655 in total, or that means 2 diameters 25 and 1 diameter 32. And for the flanks, we have for torsion reinforcement, we have then in total 4 diameters 20 or 2 diameters 20 in each side. So the red dots is torsion reinforcement. It's 2,383 divided by 8 for each dot, and then we combine it. We have seen the distance for the stirrups. We have seen that the maximum distance was 225, but now we had more than 225, so you have to repeat the calculations with a diameter 10 instead of 12 for the stirrups. And if we do that from 12 to 10, then D changes a little bit, ASV over S changes, and then we see that the distance between the stirrups, we have now diameter 10, is now 200 with 2 legs. So this is now the corrected stirrup quantity, and the corrected longitudinal reinforcement. You see that this reinforcement in the circumference is needed for the torsion, to take up the torsion. And we take care that the center to center distance is always smaller than 350. I prefer 300 millimeters. This was a calculation example of a combination of shear and torsion reinforcement. See you at next lecture.